This is Dr. Ryan Johnson with the course Introduction to Proofs, and we're doing section 3.5 today, which is about the division algorithm. So let's get started. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. Okay. I'm actually recording this on Good Friday, where you students don't have class, but that's because it's such an important day. And just a day when Jesus showed his love for us. Okay, thinking about that, heart's full, mind's ready, let's begin. We're going to skip the beginning activities because you guys are going to turn those into me later. And we'll jump down to the division algorithm. So for the division algorithm states that for all integers a and b with b greater than 0, there exist unique integers q. Here q is for quotient and r is for remainder. So we'll try to use q and r for both of those letters, such that a equals b times q plus r. So for instance, when you learned in elementary school about doing division, so for instance, if you did in elementary school, let's do it with the positive 17. So in elementary school, you might have learned to do this sort of thing. And you would have said, okay, how many 5s go into 17? Well, 3 of them do, and then you multiply them together. You get 15, subtract it, and then you get 2. And so it's kind of like this is your quotient, and then when you run out of numbers, that's your remainder, right? And so then make them negative, and we can write that answer as like -3 minus 2/5, okay? But the way, that's the way you want to do it when you're calculating, like you want to know the actual number. But sometimes for intro to proofs, we want to stay only in the realm of integers. And so to stay only in the realm of integers, multiply both sides of that equation by 5, and you get -17 equals 5 times -3 plus -2. And so then this is our quotient, and that's our remainder. But then this is wrong because we want r to be positive. And so instead, we want r to be positive. So instead we would write, not that, but -17 equals 5 times -4 plus 3. Because, so -20 and then plus 3. So this often gets students, because this is different from what you're used to, but by requiring the remainder to always be positive, we make some other things we're going to do later on much easier. So negative numbers, just know to go one further with the negative number so that your remainder is positive. Okay? Okay, moving on. So I'll do this progress check here, well, at least I'll do part of it. But the other ones I'm just going to leave for you guys to ponder, okay? So when we're dividing by 4 then, the only possible remainders are 0, 1, 2, and 3. If you're dividing by 9, the only possible remainders are 0, 1, 2, 3, 4, 5, 6, 7, and 8. And so this, and so then here, for each of the following, find the quotient remainder, and then summarize the result by writing an equation. Didn't leave myself enough room here because I was expecting, I've set it up for you guys to do on the whiteboard. So here, when 17 is divided by 3, then our quotient is going to be 5, and then 3 times 5 is 15, so our remainder will be 2. Okay? When -17 is divided by 3, in that case, we want to go past -17. So q, instead of being like -5, make it -6, and that would give us 3 times -6 is -18, so then r equals 1 to get it back to -17. Okay? So again, remember that the remainder always has to be non-negative. It can be 0 or positive. When 73 is divided by 7, then the quotient is 10, the remainder is 3. And when negative 73 is divided by 7, so just make the quotient the negative, but 1 further. So q equals negative 11, and so that'd be negative 77. To get back to negative 73, you need to add 4. Okay, and I'll leave these guys for you guys to ponder. So the numbers can get bigger and you still got to figure it out. So one way to do it is use your calculator, and like the quotient is the integer when you do one thing divided by the other thing, and then you can find the remainder after that. Okay, so here's an example of how the division algorithm helps us determine how many cases we have. So if n is an integer, then 3 divides n cubed minus n. So let n be an integer. Okay, because that's our hypothesis, right? So we start with the hypothesis, and then now we're going to inform the reader. So this part is informing the reader. We will show that 3 divides n cubed minus n by examining the 3 cases for the remainder when n is divided by 3. By the division algorithm, there exists unique integers q and r such that n equals 3q plus r, and zeros and r is between 0 and 3, including 0, not including 3. So this means we consider the following 3 cases: when r is 0, when r is 1, and when r is 2. Okay? So all of this part right here was setting up cases using the division algorithm. The division algorithm says it's kind of like even odd, but going a step further for 3 and any other number we want to do. Okay? So in the case when r equals 0, then what does it mean for r equals 0? That means n equals 3q, right? Now, I didn't introduce q there, but I introduced q here. So that's I get away with not introducing q there since it's already been kind of introduced. Okay, so by substituting this into the expression, we get, so then you just then this is a good idea of I'm telling you with English, the kind of the tricky one is the substitution, and from there it's just high school algebra, right? So by substituting, we substitute, n's become 3q's, we then expand and then factor, and we get the 3 out there. And so, hey, this is an integer, so that means 3 divides n cubed minus n in that case, right? The second case, r equals 1, n equals 3q plus 1, and then again, we're using English to kind of set up what we're going to do. So any of the trickier steps, you tell the reader what you're going to do. So the kind of the trickiest step, the one where the reader might be most confused, is when you do substitution. So we say hey, we're going to substitute. Then we do that substitution, and from there, all of these steps are just high school algebra, and so they're not worth justifying. You can expect the reader to know high school algebra. So we factored out the 3, and so since this big burrito here is an integer, the last equation proves that 3 divides n cubed minus n. So again, I could have tried numbering the equation or something like that, and then I could have said equation 1. But in this case, it was just easier to say the last equation. All right? And then the last case is when r equals 2, and that's exercise 1. I can't remember if I assigned it or not. Okay. So, properties of congruence. Theorem 334 gives us 3 properties of congruence in ways that it acts a little bit like an equal sign, right? So let n be a natural number, a, b, c, and d be integers. If a is congruent to b mod n and c is congruent to d mod n, then a plus c is congruent to b plus d, and ac is congruent to bd, and for each m, a to the m is congruent to b to the m. Okay? So our equivalent mod p is the same as equal sign, but there's no divides. Okay? You can add equations together, multiply equations together, take an equation to the nth power, but no division. Okay, so beware. All right, but everything else, it acts like equal sign. Okay, and then also when you're doing this in LaTeX, you would do something like you would write it as like, I'll write this one in LaTeX right here. So that's you do math mode, and then you do a slash I think it's congruent to b, and then slash p mod, and then if you're only doing one letter, you do space n. If you're doing something that has more than one character, then do brackets, and then whatever goes inside there. That way, if it's like you're doing mod 12, you want to use the brackets. Okay? Oh yeah, and always end your equation mode. Okay? So that's the easiest way to set up the modulus stuff so it looks right. A lot of students mess that up when they first start doing homework with modulo in it. All right, so I'm going to demonstrate for you item number 2. Item number 1 you would have done in class. Okay, so for item number 2, we got to assume the hypothesis. So starting from the beginning, n is a natural number, so let n be a natural number, and let a, b, c, and d be integers. All right, so we just assume the hypothesis there. All right, and then there's a specific hypothesis for number 2. So assume that a is congruent to b mod n, and that, oh yeah, no, we've also got this hypothesis. Okay, so assume that a is congruent to b and c is congruent to d. Okay, so then unpack that. So unpack it means n divides a minus b and n divides c minus d. Hence, and then unpack that definition. Hence there exist integers k and q such that a minus b is that, a minus b is that, and c minus d is that. Okay, now we've got into the realm of equal signs, and it's a lot easier. We know the algebra of equal signs, and so we can do stuff with that and then put it back into modulo. Okay, so we can write, like move the b and the c over. So then we can write solve for a, solve for c. And so then we can substitute. AC is substitute, substitute. Okay, maybe I should have like said substitution here, whatever. Okay, and then so then algebra, expand, and then factor out an n from the terms, from these terms. And then subtract the BD back over, so you have AD minus BC equals that. Hey, that means this burrito right here is an integer. That proves that n divides AC minus BD. So because AC minus BD is equal to n times a thing, and so n divides AC minus BD. Hence we conclude that AC is congruent to BD mod n. Okay, so how did this proof go? Let's go back over it. For first, there was a bigger hypothesis here. It took us 2 sentences to unload the hypothesis. And then we had to unpack the definitions, and that took 2 sentences because first we turn it into divides, and then we turn it into equal signs. And then from there, it was easiest to solve for A and solve for C, and then substitute. And then from there, we factored out the n, and then we packed everything back up. So like that means that get back to the AC minus BD, right? Because I want to show, this is kind of where like going backwards helps. So I wanted to show this. So I wanted to show that n divides AC minus BD. So I needed this equation. So I wanted to work towards that. Okay. All right. So that is an example of how to do these proofs with modulo. So unpack the hypothesis, unpack the definitions, do the algebra you need, and then repackage. All right, so if we were in class right now, I would have had you all prove this one on the board. And I think that's one of the sadder things about doing this with just videos, because I can often catch a lot of mistakes when you're first doing that. So just go back to my video with that discussion of the proof there if you're confused about how to do some of these proofs. Okay, Now, we're going to talk about congruence. So, theorem 3.36, properties of congruence modulo n. Let n be a natural number, a, b, c be integers. Then we have three properties. So a is always equivalent to a. That's called the reflexive property. A is equivalent to b. No, if a is equivalent to b, then b is equivalent to a. And then if a is equivalent to b and b is equivalent to c, then a is equivalent to c. Okay? So then the fact that you can swap the order, a equivalent to b implies b equivalent to a, that's symmetric property. And then a equivalent to b and b equivalent to c, then a equivalent to c is called the transitive property. Okay, because like translates. Okay, so we're going to prove reflexive and transitive. The proof of symmetric is exercise 3. Okay, so for these ones, it matters what the hypothesis is. So for number 1, each of them has a very different hypothesis. One has a very simple hypothesis, just like there's an int for every integer a. 2 has a hypothesis where you have to assume also the if. You got to assume that. And then for number 3, you got to assume both this, and then prove this guy. Okay? So pay attention to what your hypothesis is for these problems. I think that's what an issue with students' proofs in the past. Okay, so the reflexive property is almost always the easiest one, but it often involves a little bit of a trick too. So here we go. Let n be a natural number, and let a be an integer. Okay, so then we've assumed the hypothesis. All right, so we want to show, we will show this. So I'm just going to kind of unpack. I want to show that. Hey, notice that this is a good word to use when you're proving something that's seems trivial but might not be. Notice that a minus a is equal to 0, right? And 0 is equal to n times 0. So that proves that n divides a minus a, because a minus a is equal to n times a thing. Then by definition of congruence, a is equivalent to a, because a is equivalent to a if and only if a minus a is divisible by n. And we showed that. So reflexive property is always, so in this case the trick was knowing to write 0 as n times 0. So it's a very short proof if you can remember things like that about oh, 0 is equal to n times 0, things like that. Now the transitive property is going to be a little more similar to your homework because it is a longer hypothesis. So you got to let n be a natural number, a, b, and c be integers, and then we got to assume the hypothesis. So a is equivalent to b mod n, b is equivalent to c mod n. All right, so, and then that's what I'm trying to show. So now I want to unpack this definition. So unpack means that n divides a minus b, n divides b minus c. So then there exists integers k and q such that I've got this equation and this equation are true. A minus b is nk, b minus c is nq. I can add those equations together because now I'm in the realm of equations of high school algebra. So I add them together, and then look, I can factor out an n. So I factor out the n, and that means that n divides a minus c. And that means that a is equivalent to c mod n. All right, and that's what I was trying to prove. Okay, so for your homework, it'll be somewhat different to this. And what I recommend for your homework is to unpack the definition both ways. So assume your whole hypothesis, unpack all the way, and then think about your conclusion, unpack that all the way. And then once you're in the realm of algebra, you're somewhere around here, and you want to get to here, but you don't know what this thing is yet, right? And so you just got to think about what algebra gets me from there to there, okay? Your algebra will be simpler than it was in here because the symmetric property is a little bit simpler than transitive. So think about what you can do that just simply shows what you want to show. and be precise. That you have to think about how the definitions are so precise. All right. So then use cases based on congruence modulo n. So theorem, let n be a natural number, and a be an integer. If a equals nq plus r, and r is, so division algorithm, then a is equivalent to r mod n, okay? And the corollary to that is that if n is a natural number, then each integer is congruent modulo n to precisely one of the integers, 0 through n minus 1. So this is how we get, whenever you're talking modulo n, this is the corollary we use when we're talking mod n into n cases. Okay, so if we're doing modulo 5, then we can do almost anything into 5 cases, just like how we did even and odd into 2 cases. Okay? All right, here's an example. For each integer a, if a is not equal to 0 mod 5, then a squared is equivalent to 1 mod 5, or a squared is equivalent to 4 mod 5. So we're going to prove the proposition using cases. So because the hypothesis is a is not equivalent to 0 mod 5, we can use 4 cases. A is equivalent to 1, or a is equivalent to 2, or a is equivalent to 3, or a is equivalent to 4, right? Because we don't have to worry about the a equivalent to 0. So then we're going to do, I'm going to show you 2 of the cases, but not all the cases. So case 1 is when a is equivalent to 1 mod 5. In this case, we can say, we can use theorem 3.4 to square both sides, but then I know what 1 squared is. 1 squared is 1, so I'm done, right? Then when a is equivalent to 4 mod 5, use theorem 3.34 again, so remember to cite this. Cite this in your homework. Then, oh, I think I made a mistake here. I think this is supposed to be a 4. So a squared is equivalent to 4 squared mod 5, and then I know what 4 squared is, it's 16. Now we also know that 16 is equivalent to 1 mod 5 because 16 equals 5 times 3 plus 1. And so that means that a squared is equivalent to 1 mod 5. Okay? And the other cases, 2 and 3, a squared ends up being equivalent to 4 mod 5. So, but these 2 cases show you roughly how to do that sort of thing of breaking the cases modulo n. Okay, so if we were in class right now, I would have you guys complete cases 2 and 3. And again, I think that's something we're missing from these videos, is that I don't get a chance to catch whether you're getting it or not. But hopefully you get it and you're able to go back over parts of the video that you don't understand. So hope you have a good Easter. Bye.